Right now, on the far side of the sun, completely hidden from every telescope pointed at Earth's sky, an active region called AR4464 is still firing plasma into space. It left our view more than 2 days ago. It has not stopped since. And, as of today, June the 19th, NOAA's geomagnetic forecast carries a specific dated warning. Fast solar wind from a coronal hole may push Earth's magnetic field to active levels later today, with that disturbance likely persisting into the 20th before fading by the 21st. If you rely on this channel for science that's grounded in verified data and explained without exaggeration, subscribing means you don't find out about the next one after it's already over. This kind of reporting only stays honest if the people who want it are the ones keeping it alive. Every figure in this video is drawn from NOAA's Space Weather Prediction Center, NASA's Solar Dynamics Observatory, the National Academy of Sciences, and peer-reviewed grid engineering research. Nothing is inflated to sound bigger than what today's actual data shows. Where the picture is genuinely uncertain, this video will say so. So let's be precise about what's actually happening, because precision is the whole point. This is not a major storm. Say that plainly, because a channel that wants your trust doesn't get to skip the boring truth to chase the exciting one. Over the past 24 hours, solar flare activity sat at very low levels, 12 flares total, and 10 of them were B class, the weakest category that registers at all. The strongest was a C2, common, unremarkable, the kind of flare the sun produces almost daily, even in a quiet stretch of its cycle. Earth's magnetic field, measured by the KP index on a scale of 0 to 9, sat at 1 to 3. No storm thresholds were crossed. Forecasters are putting the odds of a moderate M-class flare at just 15% today, and the odds of a major X-class flare at 1%. But here's where this gets genuinely instructive rather than merely calm. The sun does not stop being interesting just because nothing severe is happening this week. Right now, NOAA's GOES-19 satellite is watching that departed region, AR4464, hurl prominence eruptions, arcs of glowing plasma the size of multiple Earths, up and over the sun's visible edge from a position we technically cannot see anymore. It went quiet for nothing. It rotated out of view, still active, and the question every solar physicist watching this region is asking right now is simple. Will it still be this active when it rotates back into Earth's view in roughly 2 weeks? Active regions can decay into nothing during that blind period on the far side. They can also rebuild. We will not know which until it's back, and there is no instrument on Earth or in orbit that can see around the curve of the sun to check early. That gap, the part of the sun we simply cannot observe, is not a minor technical footnote. It's a structural blind spot in the entire global early warning system, and it's been true since the birth of space weather forecasting. We watch one hemisphere continuously, the other hemisphere we infer. Meanwhile, the active forecast for today and tomorrow comes from a different mechanism entirely. Not a flare, not a coronal mass ejection, but a coronal hole. That's a region where the sun's magnetic field opens outward instead of looping back on itself, letting solar wind stream out far faster than the background rate. NOAA's forecast discussion specifically flags this stream as the driver behind today's and tomorrow's elevated geomagnetic activity, with conditions expected to ease back down by the 21st. This is a real, dated, currently unfolding space weather event. It is also, by every measure NOAA tracks, a minor one. Aurora watchers at high latitudes are being told to stay alert. Power grid operators are not being told anything close to that. So why does any of this matter to you if nothing dangerous is forecast this week? Because the mechanism that turns a quiet Tuesday into Quebec, 1989, isn't a different kind of physics. It's the same physics, scaled up. Here's how it actually works, and why a forecaster watching a calm KP index can still be watching the early instrumentation of something far larger. A geomagnetic storm disturbs Earth's magnetic field, and a disturbing magnetic field induces electric current in any long conductor sitting beneath it. That's Faraday's law, the same principle that runs every generator on the grid, except in this case, the unwilling generator is the planet itself. These are called geomagnetically induced currents, GICs, and they're quasi-direct current riding on top of a power grid, engineered entirely around alternating current. Feed a transformer that kind of current, and you push its magnetic core into half-cycle saturation. It starts drawing enormous reactive power, generating heat in places never designed to handle it, and in documented worst cases, that heat physically damages the windings inside. This is not theoretical. On March 13, 1989, a coronal mass ejection produced a geomagnetic disturbance rate of roughly 500 nanotesla per minute over Quebec, sitting on ancient, highly resistive Canadian shield rock that makes induced currents worse, not better. 7 static VAR compensators tripped, voltage collapsed. Transmission lines around Montreal lost synchronism and disconnected to protect themselves. Total elapsed time from first disturbance to total blackout across the entire Hydro-Quebec grid, about 90 seconds. 6 million people lost power, some for over 9 hours in March in Canada. A transformer at a nuclear plant in New Jersey, hit by the same storm, was damaged beyond repair. And 1989 wasn't close to the physical ceiling. In September 1859, a storm now known as the Carrington Event produced a disturbance more than 3 times more intense by modern reconstruction. Telegraph offices sparked and caught fire. Auroras were visible in the Caribbean. 2 operators on a line between Boston and Maine discovered they could disconnect their batteries entirely and keep sending messages on the storm's current alone. The National Academy of Sciences modeled what a storm of that scale would do to a modern, electrically dependent society in their 2008 report, and the number they arrived at was $1 to $2 trillion in damage in the first year, with full recovery potentially taking 4 to 10 years. A separate 2013 joint study by Lloyd's of London and Atmospheric and Environmental Research modeled the North American grid specifically, identifying the Washington to New York corridor, the upper Midwest, and the Gulf Coast as the highest risk zones, and projected 20 to 40 million Americans could lose power for anywhere from 16 days to as long as 1 to 2 years. The duration determined almost entirely by how fast custom-built, multi-million-dollar extra-high-voltage transformers, with no national stockpile size to replace many at once, could be sourced and installed. That is the gap between today and that scenario. Today, a coronal hole stream, a KP index nudging toward 3, an aurora at high latitudes. That scenario. A direct, fast, well-aimed coronal mass ejection from a region with the kind of magnetic complexity that produces major flares, the kind AR4464 has not shown this week, and the kind no one will be able to rule out the moment it returns to Earth's view. Here is the honest, uncomfortable scientific reality underneath all of it. We can watch the sun continuously on the Earth-facing side. We can track coronal holes, measure solar wind speed, and model a CME's likely arrival window once it's been observed leaving the sun. What we cannot do, what no instrument built so far can do, is see around to the far side in real time, or predict with certainty how an active region will evolve while it's hidden there, or know the precise severity of a storm's impact until it crosses a satellite roughly 1 million miles from Earth, somewhere between 15 and 60 minutes before it arrives. 15 to 60 minutes is the entire operational warning window grid operators train for. It is not a comfortable margin. It is the margin that exists. So here's where today actually leaves us. Nothing severe is forecast. The numbers are calm. But a known active region is still venting energy from a position no telescope on Earth can currently see. NOAA's own forecast has a dated, specific elevated activity window open right now through tomorrow, and the physical mechanism that turned 90 seconds into a 6 million person blackout in 1989 hasn't gone anywhere. It doesn't take a rest between events. It's running in the background of every quiet day exactly the same way it's running today, waiting for the one alignment of speed, direction, and magnetic orientation that turns a routine forecast discussion into the next dated entry in that same historical record. The sun doesn't know what day it is. It only knows what it's doing right now on its own side where we can't see. And somewhere in that hidden hemisphere, the region that just left our sky is still deciding what it's going to bring back with it